So welcome everyone. This is a new edition of our distinguished lecture series at the Max Planck Institute for the Science of Light. So this is our main scientific event. Before we start, I remind you that this talk will be recorded. So by participating, basically you're tacitly agreeing to the recording. And please mute yourself. And if you have a question, you can either write Q in the chat, and I will at some point tell you to speak up, or you can directly write your question in the chat, and I will do my best to read it. So it's a real pleasure to have today with us Professor Michal Lipson. She's a professor of electrical engineering and applied physics at Columbia University. She did her PhD at Technion in Israel, then went on for a postdoc at MIT, and then after a professorship, as I understand, in Cornell, she moved on to Columbia. So she's a pioneer in silicon photonics, has gotten many prizes. She's a member of the National Academy of Sciences, also got a MacArthur Fellowship. And she is the first woman to be awarded the John Tyndall Prize for Photonics in 2021. And she's been consistently ranked as the top 1% highly cited physicist. So it is really a pleasure to have you with us today, and we are looking forward to your talk.
Thank you, Sylvia, and thank you everyone for being here. It's like I said, it's a pleasure to see many familiar faces, especially during this time. Okay, can you see?
Yes.
Okay. So today we are experiencing a complete revolution in photonics. If we look 10 years ago, we still used to work with discrete component, with fibers, with lenses, if you wanted to build a optical system. Today, you can send your little CAD, your little design, where everything is integrated, and print it out lithographically. You can have thousands and thousands of components in a little chip, and that's basically completely scalable. So think about silicon photonics the way we think about VLSI. We used to have individual components, individual transistors, and today it's all integrated. Silicon photonics and photonics in general went through this revolution. So I'm gonna tell you a little bit about the history, and then I'll give you a feeling of the challenges that we are now experiencing. One of the reasons why silicon photonics was so successful is the incredible demand that we needed. In early 2000, there was a kind of a cry for help from microelectronic industry. And they realized that when you actually transmit information using traditional copper wires, you are limited in your bandwidth. Why? Because if you try to pump more and more data, the dissipated power is going to shoot up, and it's not going to be feasible. You're basically going to cook up your computer. So the idea here is not to do any computing with photonics. The idea is to transmit data over photonics. So that's where optics is really powerful. Incredible amount of data, incredible amount of bandwidth without any power dissipated. That's the beauty. And today, silicon photonics is being introduced in all data centers. So basically, we're talking about rack to rack and within a rack. And now more and more is being introduced on the board itself. So the advantage of photonic is for large distances, but it's getting more and more into smaller distance, just because the bandwidth that you need for this system is incredibly high. We're talking about tens of terabit per second that are running on the board. So what were the challenges? So when we started working on that, there were many challenges. Silicon was a electrical material, not an optical material. And one of the problems that we had to circumvent is simply the fact that in silicon, light is extremely confined. And that has to do with the dielectric contrast between the silicon and the oxide around it. So if you look at waveguide theory, for you to send light into these waveguides, the waveguide itself needs to be extremely small if you want to send it without any loss. So that's the size of the silicon. And that is not even to scale, is the size of the fiber. And when I started my career, this is what we did. We just, what so-called butt coupled, just put it one against the other and did some praying, and some of it went through. Remember, I get this question quite a lot, so just I'm preempting it. Maxwell's equations are reciprocal here. So whatever goes in one direction goes also in another direction. So the same problem is from a fiber to waveguide and the waveguide to fiber. So the way we overcame this problem was to take the waveguide and make it even smaller. So start with a waveguide and think about kind of a pencil where you have a tiny tip at the end, like that. And when you do this, all the light from a fiber, say, will seamlessly couple to the waveguide. And the reason why this works is that by making that taper, you are delocalizing light. So you are engineering the optical mode, and that's the beauty here, that you can really control the shape of the mode of light. And so you start here with, you start on the left with highly confined light. And then as it propagates, it gets more and more delocalized. And here, the shape of light is just like the one of a fiber. So as far as light is concerned, it doesn't know really if that this is a little tip. The mode here matches beautifully the mode here. And then we usually clad it and with the oxide, so it really looks like fibers are really oxide. So it really looks like a fiber, or behaves like a fiber. And so if you want to know, for example, what is the tolerance of this alignment? Do you really care that light is exactly at the center of the fiber? No, you don't care, because it behaves like fiber. And when you align fiber to fiber, is pretty tolerant. It's really on the order, the tolerance is on the order of the fiber diameter. And here, this alignment tolerance is basically the same. The second challenge that we had is how do we actually modulate light? And that was kind of very important because basically the idea is to get the ones and zero of the transistor, 1 volt, 0 volt. That's actually what produces the data. And connect it directly, hopefully without even amplifier, directly onto a optical chopper modulator that either sends light or doesn't send light. So really what we are looking for is a material that has a electro-optic coefficient where you apply your voltage and then it becomes transparent or opaque. And there are many materials like that. Gallium arsenide, lithium niobate that have strong electro-optic coefficient that we can build such choppers out of them, modulators out of them. Silicon is not one of them. Silicon is completely symmetric, does not have an electro-optic coefficient. So we had to really work hard to how to convert this silicon to an electro-optic material. We had to stick to silicon because it had to be compatible with the microelectronic industry for it to make an impact on that industry. And the way we solved this challenge, was to rely on a very small effect. It's called free carrier a plasma dispersion, where basically when you change your concentration of electrons and holes in the material, it changes a little bit the dielectric constant. It's a very minor effect. It kind of changes the index, the fourth digit, like instead of 3, it becomes 3.0001, okay? But we amplified this effect by using a resonator. It's like a cavity, but in in integrated fashion, we don't use 2 mirrors like a Fabry-Perot. Instead, we use a resonator like you see here. Light goes here in this waveguide, and it travels here for a long time. And basically what we are doing is recycling light in the resonator so that it can experience quite a lot of these carriers plasma dispersion. So now today there are silicon modulators that have like 50 gigahertz, all based on carrier injection and depletion, all by changing the carrier dispersion. So based on these demonstration, this field exploded, and it exploded in a single decade. It started with a few theoretical, a few papers, and it kind of went to industry already very quickly. Today, I still remember people in the audience saying that silicon photonics will never work. And the reason why they said that, because silicon really didn't have an electro-optic coefficient. It was pretty lossy. So when you sent light into it, a lot of it got lost. But we made it work. And today, a lot of the devices that we have are much better than the traditional materials. And this has to do with the fact that we are leveraging a fantastic process. If you try to make, and I'm going to talk a little bit about it later, if you try to make fabricate a little sidewall or a little boundary, if you make it out of gallium arsenide, microfabricate it out of gallium arsenide, it's going to be pretty edgy, like jaggedy. If you make it out of silicon, it's going to be beautifully flat. It could be less than 1 nanometer on average, jagged. It's really beautiful, and that's what makes the performance of these devices so high. So where do we stand now that I sold you that silicon photonics is the best thing since sliced bread? Now, where do we stand today? What are our challenges? So the way we send data in, let's say, a data center, we have all these lasers, individual lasers, just like here, each one with slightly different wavelengths, slightly different color. They go into a silicon chip where the modulators are. So this is how you send data on each of those colors. Then you combine them all in the silicon chip, and they travel through a fiber. And then you have the opposite of this, but now with detectors here. So you demultiplex, send data to each one of the detectors on the other side. Okay. The main problem that we have is that this system is not scalable, really. Each one of those lasers needs to be bonded, needs to be aligned. The actual frequency needs to be just right. So because it's all on a grid, it needs to be thermally stabilized. And it cannot have any crosstalk with its neighbor. So today, the maximum, this is called the WDM, wavelength division multiplexing. The maximum that you have, the maximum of wavelengths that people have worked with is not a lot. The ones that you can buy is 8 wavelengths, basically. So I'm going to show you a few solutions for that we are working working on. Well, the first solution is to take one of those lasers. You only need one. Make a special chip, which I'm going to tell you what it is. And out of that chip, automatically, you will have on a grid different wavelengths. Okay, so it's a special chip that needs only one laser to generate all this array of lasers that I just showed you. Right? So by doing this, you could have 100 different light sources. So this wavelength here, the chip here, is a nonlinear silicon photonics. So there is a parametric process that is happening here on the chip that generates these wavelengths. So this is work together with Alex Gaeta, where light is sent, single laser is sent into the chip. This cavity that I showed you before is the same cavity here, but it's specially designed. The dimensions need to be just right, and I'll explain that in a minute why. And there is a parametric process going on here that has some gain. And then with the feedback, so you have a gain, you have a feedback, this whole thing oscillates. And it reaches a stable point where all the wavelengths are generated and are locked in wavelengths and in phase. And so this is an example of all the wavelengths that are generated. You see here, each individual point here is one wavelength. So today there are many labs working on combs, it's called micro combs, based on silicon photonics. And I should say that when I say silicon photonics, I say it in a broader term. So it could be, for example, silicon nitride, silicon oxide, all materials that we can actually fab in a external fab, in a foundry that could be massively fabricated. So it's all silicon based, but not necessarily silicon. And the reason why these are, I told you that there are many people working on those combs. So the application is for data centers, but not necessarily. These combs are fantastic for metrology, for sensing, for spectroscopy. So there are more and more applications emerging based on the fact that we can generate these enormous bandwidth, basically almost an octave of light sources, individual light sources. So now the idea is that you take each one, you peel it out, and you modulate it. So I told you that when you design the ring, you have to be careful. The dimensions need to be right. So what do I mean by that? The reason why silicon photonics, in this case is silicon nitride, is so interesting or so powerful for nonlinear photonics is not only because of the nonlinearity of the material, and not only because I'm confining light and then I have effective nonlinearity very strong. No, it's because of the dispersion of waveguide dispersion. The dispersion is independent of the material. So if I take a waveguide, if it's highly confined, it looks like that, but there is a lot of kind of light outside. So if it's tiny, it senses a lot the material outside, and the effective index is going to be very low. If I do this, I take a very large waveguide, light only senses the waveguide material. So the effective index is going to be high. So you can see already that just by changing the dimensions of the waveguide, I can have a very strong dispersion, very strong change in the group velocity. So that's only happening in these strong index contrast material. It doesn't happen in glass waveguides, in fibers, and so on. So if I have a material that have a terrible dispersion, crazy dispersion, and I can't do any nonlinear process with that, and we've all encountered materials like that, where the dispersion is so high that I can't mix any colors. Different wavelengths will propagate at completely different speeds. And therefore, I can't mix them. I can't have any nonlinear photonics. So let's say I have this material, I'm not worried. I can compensate the dispersion by using the waveguide dispersion, by changing the dimension of the waveguide itself, so that the waveguide dispersion compensates the material dispersion. So that's the power of these microcombs. But there is a secret that nobody is really have been talking about, is that all these microcombs that people work on, including ourselves up until 3 years ago, they require a huge laser to pump and generate all these combs. It never looks like that. This is what I would like. I would like one amplifier or laser pumping the resonator. I don't want a huge laser, right? So why do I need so much power to pump the comb? Why can't I have a small laser with low power pumping it. It's because the threshold for oscillation, the minimal power that I need here, depends quadratically with Q, with the quality factor, meaning the less power I have, the less losses I have, the higher the Q, the less losses I have, the less power I need. So the way to get this to work, this vision to work, is to decrease the losses as much as possible. So where do these losses come from? These losses are not material losses. They are really just interface losses. So if you have a jagged interface, light will scatter out of it. And that's really still the case. I mean, people have thought that we've reached a situation where we have a very, very nice boundaries. It's still the case. So what we are showing here, and this is William from my group, he's shown the following. If you just deposit a silicon nitride, and this is deposition kind of it. This is LPCVD. This is furnace. It's supposed to be the best ever. Okay, very high temperature furnace. This is the surface. So it's 1.59. Right? Now, if you do some treatment, and here we are doing CMP, basically mechanical polishing, you can get down to 0.3 nanometer. Now, 0.3 nanometer is on the order of 1 atom on average. So the one on the left is as deposited. This is usually what we use. And the quality factor is high, but not that high. We still needed that laser to be pumping it. But the one on the right is the one that we are now working with. Basically, all the surfaces have less than 1 nanometer fluctuation, usually much less. And if you want to read in details what are the processes, we describe all the process. But the bottom line is that the quality factor that you can get here is extremely high. So the typical losses that we get now is 0.1 dB per meter. So it's extremely low. These are example of waveguides that you can, this is basically almost a meter of waveguide all packed in that tiny, tiny little chip. And it's a waveguide wrapped around and then get out, and then again wrapped around on the chip. And if you make a resonator out of this, the quality factor can be up to 60 million, maybe even 80 million. So it's really unprecedentedly high, extremely high. And now, when we have that extremely high resonator, we can go back to our vision, put a little RSOA is basically just a bad laser or a low power laser. And what the resonator does here, it provides a cavity from the resonator to the back of the RSOA of the laser, and it self-injection, it injection lock this amplifier, and this whole thing pumps. Now we have one wavelength achieved because of this injection lock, and in the same ring, it also generates the comb. So the beauty here, we now routinely can injection lock and get beautiful one wavelengths out of this. And if we design the ring correctly, we can also get the comb out of it. So it's a easy way to clean lasers that are dirty, that have a lot of modes and noise. And it's also a beautiful way to actually generate combs out of these cheap scales. And we use actually what Brian, my student, did. He just for the heck of it, he used a couple of batteries, AA batteries, to pump this to actually provide power to this chip, and he ran it for 24 hours, just to show that we really could integrate it all. So that's the battery operated frequency comb, and it's all basically, this is the size of the chip. We don't need it. We don't need all this. We only need it for just to hold mechanically. But the little chip is here. Actually, it's AAA battery. Okay, so I told you that right now we have all those lasers that hopefully will be generated from a comb, and they go through the fiber. But we can do even better. There is a secret for silicon photonic that there isn't for other platforms. It's the fact that we have all those spatial modes in those waveguides, and they are robust, meaning that, you know, if you the way you design it, and if you bend light, for example, if you bend the waveguide and you do it right, you're not going to excite any other mode. And I think a lot of us have worked with fibers and are scared of modes, because we know that any multi-mode waveguide, as soon as you breathe on it, provide any strain, any change in temperature, the whole modes, all of the modes mix. But in our case, the modes, because of this strong confinement, the modes are very well separated. Meaning the effective index of each one is very different. So they don't mix so easily. And everything is determined by design. So why am I excited about this? Because this, if I can, for example, have control of, let's say, 6 modes like these, 6 modes will give me bandwidth that is 6 times that. Because at each mode, I can send light at all those wavelengths. So it really, I should not only multiplex in wavelength, frequency, we should also multiplex in modes, spatial modes. So in order to work with modes and not just work with modes that are very low, we have to be able to convert back and forth between, let's say, the first order mode and the 9th order mode, okay? This is an example. But this 9th order mode, and the modes are very high, they are embedded almost in a kind of in a semi continuum. There are many modes here. So in the lowest order mode, the modes are very separated. But once I get to higher order modes, they are not. So so the question is, can we only work with lower order modes, or can we actually go to the higher order mode as well? My student, Utsav Dave, he came up with an approach on how to convert from a low order mode to a very high order mode. He converted up to 12 order mode by doing adiabatic. But when you think adiabatic, you think about change, linear change usually. That's very slow and long, right? Long here in the size. We are not talking about that. We are talking about adiabatic in the sense that the conversion at every point here, the probability of the mode to convert to any other modes except the one I want is low. So what you see here is the change of both this waveguide and this waveguide. And also often we change this space. And I'm going to tell you what's the recipe here. So what we need is to convert, let's say, for example, this mode to this mode, okay? So this is the gap, and this is the effective index. So the gap changes with Z and with propagation, and the effective index also changed with propagation, okay? So these two photonic states, what do they remind you? They remind you of electronic states or atomic states that you wanna basically, as a function of time, pump it up, so provide a function in time that will convert the lower order mode, will hop to the higher order mode, even if there are many other states nearby. So this problem was already solved. In the atomic physics community, it's already solved. So we just need to convert the time to Z. It's really the same equation. There are many functions as a function of time that show that are very good for this adiabatic conversion, are very compact. And we just take one of those functions here, and we convert Z from time to Z. So the way the gap changes and delta, the effective index change, they change in a very nonlinear way, and it guarantees that along the whole path, the conversion is adiabatic. And note that if you try to do linear changes, there will be a point where the conversion is not adiabatic. And usually these are the losses in the mode. So this can be very compact. So now that we know how to deal with mode, this is an example of what Utsav did. He converted the first order mode to the 8th order mode. This was kind of, for those of you that are not familiar with the literature for this is kind of unheard of. Actually, when I talked to Utsav and I said, let's work on that, he asked me, what would be a good number of conversion? And I said 8. I just pulled it out of my, just wanted to show something that is really very hard, because if you look at the literature, really you have up till 3rd order mode. That's the most common. And recently he also showed 12th order mode. So that basically now we can go back and forth between these different modes. So I'm gonna, so I told you why this is very exciting for data center. So now we have lots of opportunity to send a lot of data using combs and using modes. The mode is very important also for completely different applications. And I'm just going to pick one to show you. Actually, both the comb and the mode, but I'm going to concentrate here in the mode. So one of the hardest thing in photonics is today is Lidar for vehicles. Basically, the idea is that you're going to send light. This is a Google slide from Google where they have this huge thing on top of the car, like a baseball thing, and they have a beam that scan, and when it hits a target, there is a little bit of reflection, which interferes with the light that you sent, and then this signal is analyzed, and you can tell where the car is and how fast it's going. But if any of you have worked with interference systems, you would know that any variation, any change, you breathe on it on your interferometer, if it's free space, and all the fringes are going to move. So can you imagine that you have this system, interference system, that is on the car and it's moving? So this is really a heroic engineering feat, and that's why it costs as much as the car. So we are working on sending light out of a little chip, basically miniaturizing the whole system, sending it out of the chip without any moving parts, and controlling it electrically to move it. And I should say, for disclosure, that I have a company on that, but it's based on work that we've done in my group. So that's the idea. We have a little chip that will emit the beam. So how does it work? So you take light from outside, you send it into a waveguide, and then you split it into the different waveguides, where each waveguide has a controller for the phase. So for example, using carrier dispersion or the thermal effect, you can change a little bit the index of refraction. Now, it turns out that the waveguide, because it's so confined, it really emits or transmits light like a dipole, the pattern. So outside in air, it looks like a dipole. Now you put them very close together, took all those waveguides, all those dipoles close together, and you are forming a beam. And if you want to move the beam, you change the phase of the waveguides, one relative to another, and the whole beam moves. So we have done that. We have actually demonstrated a system that is very large, but I'm going to show you that we had a challenge, a big challenge to overcome. So the big challenge that we had was each one of those modulators consumes a lot of power. Even if you do thermal optic effect, you do carrier dispersion effect, it does consume a lot of power, which means that it heats up the whole system. And the whole system becomes unstable because the effective index changes with temperature. So not only that the problem is the actual power, the system itself doesn't work. So we had to come up with a way to modulate light, meaning change the phase with low power. So one of the ideas that we thought about is, okay, let's use a resonator or a cavity where I'm just basically circulating light. Should work. But for these systems, I can't have frequency dependence. So it has to be a modulator, a phase modulator that has no frequency dependence, and all cavities have frequency dependence. So let's take a step back. Why do cavities have frequency dependence? They have frequency dependence because you are taking the same light and recirculating it. So it interferes with the light that went in. So all those lights here, they interfere. One way for them not to interfere is to send light in here and send this light at a different state, at an orthogonal state that doesn't interfere with the first one, okay? So what are the possible states? Frequency, which I don't want to work with frequency, and modes. So the secret here is to send light into one mode, take it, and convert it, and send it back. And do it again. Take it, convert it to another mode, and send it back. And then at the end, convert it back. This doesn't show here, but convert it back to the first order mode. So all this would be seamless. Nobody knows what's happening inside. I'm sending light here, and I come out here, but the phase of this is enhanced by the number of modes. So that's the idea here. Basically, I'm propagating all those modes in this waveguide, and I won't get too much into detail here, but you are sending light here, sending light here, and then convert it to another one and send it back in a different mode. And all other modes don't sense it. So we actually did it for 7 modes, and we've shown an improvement of factor of 10 because some modes are more confined than others. So it turns out that it scales at a minimum with the number of modes. We actually built the phase, phase array, the Lidar system based on that light recycling technique. And what I ask Chris and Steve, my students, to do is to show that their system is much better than, let's say, a movable mirror, because ours is much faster. Movable mirror is limited in time, always mechanical. So in order to show this, Steve is actually a musician. So let's see if I can get it to work. You have to believe me that there is a beautiful concert, and the beam is moving with the notes. So I spoke mostly about data centers, a little bit about LiDAR, and a little bit about the nonlinear optics, but there is a whole range of of areas that have been enabled by silicon photonics. I didn't get a chance to talk too much about it. The modes are fantastic tools for synthetic dimensions. If some of you are familiar with topological photonics, we are now integrating different materials on silicon photonics. I saw my student in the audience who actually is doing this fantastic work. This is a Nature Photonics that we just published, Ipshita Data. She's just graduating from my group, but she's integrating different materials, 2D materials on silicon photonic waveguides. Okay, so I'm gonna stop here. These are the folks who actually do this work, and these are the agencies.
Thank you. Thank you very much for the very nice talk. So yes, please, if there are questions, as I said, you can either write them on the chat or yes, to the queue. So yes, Masha.
Yeah, thank you. Wonderful talk. Do you also look into the compounds of silicon X, nitrogen Y, like different combinations?
So, for example, silicon-rich nitride, or silicon, yes. So there are actually quite a lot of people working on that. We actually think a lot of our silicon nitride is silicon-rich, but we are not controlling it methodically. I can't really say. I can't really say. There is a price to pay with silicon rich, and it's really the losses. And you end up there's a lot of impurities when you end up working with silicon rich.
Thank you.
There is a question from Sven, I would say. So how high can be the highest clocking at state at the moment? So right? Yeah.
The highest clocking. Now we are regular computers now at, let's say, 4 to 8 gigahertz, a personal computer at home. And how high can be the clocking in future? Because silicon photonics is also interconnected with quantum computing, and I could imagine.
Yes. That's a very good question, because if you have to be at least that, or on the order of that. If you're much higher, then it's pointless. Yeah. Because you need to be. You need to translate your data from electrical to optics. So there's no point of being in optics much higher. Yeah. But the data is usually multiplex, the electrical data. So the actual data that is coming out of the chip is much higher than the clock data. Is right now it's about terabit per chip, electrical chip, and you have multiple processors, and they are all synchronized, and so it's not the individual clock anymore. Yeah.
Oh, I see. Okay. Thanks for that.
Thank you. Could you speak on the prospects of the silicon nitride platform for visible? Yes, I couldn't. I had to choose. I had to have one team here, and I didn't. The loss are certainly not anywhere close to 0.1 dB per meter that you get at 1550. This is Amit Agarwal. Let's see. The reason why Amit is saying that the visible is much more lossy is because the scattering goes like index contrast to the fourth. and the wavelengths to the fourth. So the lower your wavelengths, the higher because it's really scattering. So you're right, but if the interfaces are extremely good, you can have low loss in the visible, and we now have a few million Qs in the visible, like extreme visible, like blue. And we are working on systems in the visible. A lot of them are require a pretty complicated system. So it's fun for us to think about how to solve it. Hey, Joyce. Good. Thanks for the great talk. My question, if you consider two spatial modes that do not couple, can you modify the waveguide so that the symmetric and antisymmetric superposition of the initial modes are now preserved? Let me think. So if you consider two spatial modes that do not couple, right, can you modify the waveguide so that the symmetric and antisymmetric superposition of the initial mode are now preserved? Okay, yes. So that is why, that's a very good point, because that is why when you just take two waveguides, parallel and identical to each other, then you have two possible modes, the symmetric and the antisymmetric, and easily they can couple to each other. If you don't want it, then the way we are doing, we are slightly modifying each one so that they are not completely symmetric, but the rate that we are modifying is just right so that it is adiabatic. So that you don't have to change it a lot, just a little bit, and you change it with a rate that is just right.
Okay. Thank you.
Hello, ma'am. Here is Vikas from IT Delhi. I just want to
Yes.
ask one question, like in the similar question I had asked by Lewis. Basically, if you have adiabatic coupled waveguide, basically, so what will happen? You have taken a particular profile there for that adiabaticity. So what will happen if you take care? Have you taken care of these temperature based profile also there, like?
Say again, because say again.
Ma'am, basically you have done in basically the coupled adiabatic coupler you have taken. So
Yeah.
you have taken a profile there
Yes.
for that particular adiabaticity to get 8 volts.
So
there.
you are saying, can
Yes,
you get that profile with temperature?
Compared to like, can we get that with the help in the temperature development dependent also there? Yeah.
Yes, we are working on that, and the temperature, you have to work. Really, the effective index that we are changing, if you look at the profile, the effective index, we're changing from 3 to 1.5. It's hard to get a temperature. It's possible, but it requires real. It might require, for example, to dig holes, to isolate, in order to get very, very strong temperature in one location and no temperature in another, because the contrast is relatively high. But thanks for asking. Yeah. It's a good idea.
Thank you, ma'am.
Yeah.
Yeah, thank you.
So it seems that we missed a question. What is the advantage from MPI Halle? What is the advantage of the device shown in slide 32 to a device in which the waveguide is physically folded 8 times?
What is the advantage? It's if you are folding it 8 times, you have less power by a factor of 8. It turns out that you have it's really the same advantage that the resonator provides. You are recycling light, and the effect is much stronger. So you can, for the same amount of power, you can get a much stronger effect, or for the same effect, phase change, you can get it by much lower power without paying the price on bandwidth. So it's good for any wavelengths.
And there is still another question in the chat. Is there any stress issue for the silicon nitride deposition with LPCVD?
Yes. So LPCVD is a high temperature deposition. It's what a lot of people use for the combs because it's the lowest losses. And yes, there is. And that's why it took quite a bit of time to develop these. When we deposit nitride, there is nitride deposited also in the back. And then if you check our papers, we really give the whole recipe. And then when we deposit usually in 2 rounds. So we do one, the top and bottom, so that the wafer is not bowed. Then anneal it, relax it, and then deposit the rest of nitride. But this took, you have to be careful with that, yeah.
There are no more questions in the chat, so maybe I take the chance to ask a question myself. So yeah. I was wondering, you were showing this application with the Lidar, and I was wondering, so you were talking about, you know, it seems quite, it's almost as big as the car. Yes. And I was wondering how, when you go to miniature or to make it smaller, how much do you have? So what about the sensor? Is it also so?
Yeah, the sensor is really a kind of a Mach Zehnder, because you are really beating it with the input light. So and the one that comes, and this is a little counterintuitive, it's hard to believe, but it works. The light comes out. It's intuitively for us, it's easy to believe that light would come out, it will interfere and form a beam. But it's not so easy to believe that will reflect and will be, but it's symmetric, it does.
Thank you. Let me see. Okay, I think we are now not missing any other question. So thank you very much.
Good. Thank you, guys.
for the very nice talk. And yeah, just remind everyone that in 2 weeks there will be the last edition of this semester series. So please join for the next time. So the last time for this semester. So thank you very much, and bye-bye.